All right, welcome back, everybody.
We're ready.
We're all live, yeah?
Yeah.
All right. So I think we're doing very well. We're more than halfway through the class. Lecture 14 to me, that's like, 26 lectures in the class. We just passed midpoint, So, but it's a time, I think we've locked in a lot of good core tools and good core skills, and there are more that we will try to lock in about motion planning and task level planning in the future. But I want to take a step back and remind us that actually there are a bunch of problems that we're not solving very well yet. And so this lecture, I think, compared to some of the others, is really more. It's not yet a recipe. This is a work in progress, I would say. This is research that's happening, around the world right now, and it's the edge of what we know how to do. So I hope you guys, unmute and talk and everything like that. But I want to talk through some of the sort of really hard problems. And let me start by just laying it out there. So I think one of the biggest, hardest problems in manipulation is we could call it a lot of different names, but I would say it's the problem of state representation. Okay, so we have our perception system, and the thing we feed to our perception system is sort of clear. We have sensors that we're reading, and we're going to send that into our perception system. And we're going to get better and better at writing pretty good planning and control systems. And the output of those are sort of clear. It's whatever I send to my actuators. We've talked about positions versus torques versus whatever, okay? I want to talk about that channel in between right now, okay? What is it that the perception system tells the planning and control system, right? What is, if you've got a perception team, you're trying to build some complicated robot, you've got your perception team, and you've got your planning and control team. Maybe each of you self-identify in one camp or the other, maybe you don't, maybe you spread the two, but there's good reasons, and I'll talk about it a little bit, but there's some good reasons why I think it makes sense to ask about those as two separate boxes. And it's a super hard question to say, what should that signal be going in between, right? So, if you're I would actually say this is one of the biggest reasons why I am very excited about manipulation right now, because, if you're a walking robot, or if you're a UAV flying through the forest, or even an autonomous car, my autonomous driving friends are going to chase me down for this one, but then to some extent the question is relatively clear here. If let's just say I'm a UAV in the forest, then really, if I know my position and velocity, maybe the airspeed, right? And I need to know where the trees are. The local geometry, the local map, right? Then, I can write an estimation perceptions toolbox and have the specifications well-defined. The better they can estimate the velocity, airspeed, where the trees are, then the better I can write my planning and control system, and life is good. Even if I'm a autonomous car, right? So at some point, I need to know exactly where the stop signs are, exactly where the traffic lights are. I need to know where the other cars are, how they're moving. Somebody somewhere has to solve this super hard problem of like, what is the other driver thinking, and what's he going to do next? But it's at least summarizing my current sensors with like the positions of the cars, the positions of the lanes, that's pretty clear in some sense. For walking, sort of the same thing. Okay. In perception, in manipulation, it's really not clear. And if you hang around with me, you realize I have like 4 examples, maybe more, but I have like a few examples that I always use. And let me just throw them out here. Just to make you think about, like, what would the answer for these questions be if you are, trying to do, something like this, right? Tying your shoes, right? So what the heck is the signal, that I have to send from my perception system to the planning and control system to summarize the state of the shoe? And you could argue that it should be like some approximation of the infinite dimensional state of the rope, or maybe it should be something very topological about the where the loops are, or something like that. But we don't know, and we don't know how to write good control systems that exploit that information. Okay. What's the state of the onion when I'm chopping it, right? That one's coming. Yeah, that's number 3 or something. So yes, so what's the state of the onion, right? So we've talked a lot about the rigid body state of being like a pose, positions and velocities, but how many positions and velocities do I have to track for this onion, and is it changing constantly? At some point, I think people probably stop thinking. I asked the cognitive psychologist, and I said, okay, I start chopping an onion, and I have 1 part. Now I have 2 pieces. Now I have 3, and then I have like 100 pieces. When does it stop? What changes? And they're like, well, of course, it just stops being individual rigid bodies. It starts being a pile. It's like, okay, but how do I code a pile? Like, how do I represent a pile of stuff, and how do I write its dynamics, for instance, right? My mouse is confused. Okay. Okay, let's say I'm spreading peanut butter, right? Or there's any number of food preparation, like I'm making a salad, or I'm making pasta or something like this. Like, what is the state of the peanut butter? And this is when it kind of shows you that how force control clearly matters. And there's something about, like, probably, this person is putting it on more thinly than my kids like. I would have just on there, but both of us, I think, are using a significant amount of perceptual information, tactile information, force feedback. I don't know how to summarize that in a vector that I can send from my planning system to my control system. Oh, I left the volume on this one, sorry. But here's the buttoning the shirt one that Dale said. Yeah. So this is actually, I like the volume on this one just because she's describing a very simple strategy that could help. This was actually to help people that are visually impaired figure out how to button their shirt, right? And okay, if the first step of this is to estimate the whole state of my shirt, then something's wrong, right? Somehow I should only need to estimate something very local. In fact, the words she's using are, I'm going to use 2 fingers, I'm going to feel the button on this side, I'm going to stick my finger through, I'm going to feel the button on the other side. Okay, but how do we get that, right? So there's a bunch of manipulation tasks that I think really should be in scope, and they're just not with anything we're talking about yet. So the whole problem is just kind of too big to even think about, but I do think that there's a subset of this that is a little bit more approachable, and that's what I want to talk about today, which is this notion of category level manipulation. Let me say a little bit more about why it's reasonable to, let me justify that sort of decomposition, right? So you might argue that you shouldn't break down planning and control, and that the way to do this is just to have one big neural network or whatever that takes sensors in and spits commands out. And I think that is potentially a good idea, and we'll talk a little bit about that certainly in the class, maybe today if we get to it. But even the people who sort of advocate for sensors in, huge neural network in the middle, actuators out, wow, that went badly. Torques out. Then if you look inside there, they still have a problem to solve, which is that the perception part of your network is so data hungry that in practice, it becomes important. If you look and sort of zoom into the systems that people write in this space, they will often have an image coming in to some perception network. with some representation. And this is the question that we have to answer then. And then they'll have some other, channel that comes in for, let's say, the joints of my robot. And this goes into a relatively small neural network or whatever, and outputs torques. Okay, and this, you'll see this architecture over and over again. And the reason that architecture tends to be common, even if you're going to train it end to end with reinforcement learning or some other approach, imitation learning or something, just because you want to, for instance, pre-train on ImageNet or pre-train on Coco or whatever, it's very common to have this separate decomposition here, okay? And then again, the question is just sitting right there. And you can try to learn those. I think that's a good idea. We can try to think about physically intuitive things. Okay, but that is the question of state representation, is what should those arrows be? So category level, in my mind, is biting off a little bit of the problem. So what have we done so far? We've done two cases, really, I guess, two extreme cases. One would be known rigid objects, right? Where we have like the URDF file and it's, a Cheez-It box or a mustard bottle or whatever. So we sort of know everything about it. And then we could imagine doing pose estimation and trying to use that as our information that we're going to send across the perception from the perception system to the controller. Another case we've looked at so far is the case where we don't care what we're just going to do clutter clearing. And so we're actually not even going to bother trying to estimate pose of anything or see what objects are there. We're just going to pick up based on the point cloud only, okay? But there's something in the middle there, which is I want to do something meaningful with the task. If in the clutter clearing example, we could only just pick it up and then drop it, and we had no idea if we were picking up one object or two. It was very general, but it was very limited in what it could accomplish in terms of task specification. So category level for me is, let's take those nearly rigid objects, but try to do a whole group of them, right? So for instance, what if you want to do mugs like we've seen dish loading, this is another different example of mugs, and you want to do something specific with them. You want to hang the handle on the rack. That's a kinematically precise requirement to write or task to write. Okay, but you want it to work for every possible mug in the scene and mugs you've never seen before, right? So there's some diversity of objects in the world. We'd like to summarize them in a way that's useful for manipulation, but we don't have like a URDF file for each one, okay? But we also don't have to solve like my shirt yet. Okay, so that's the that's the setup for today, is this intermediate step of let's try to understand what we should do with category level manipulation. And I think it's a growing topic. You'll see it more and more in the literature. The title of category level, certainly in the perception literature. By the way, there's something kind of frustrating. I told you before, if you phone a friend and you ask your dynamics friend for help, right? Then they'll come back and say something about Coulomb, or maybe something that was in a paper in 95 or around 2000, and we've been thinking about it for 20 years. The problem is in this field, right? If you ask your perception, if you call up your perception friends and ask them, what do you think about state representation or whatever, they're going to send you 10 papers that came out on arXiv in the last 3 days, and it's a very noisy, exciting time, but a very noisy time. So I feel like I have to caveat that the things I say today might be obsolete in a week, but I'll do my best to try to tell you my understanding of what's happening at the moment. Okay, so let's think even about the mug case. It's sort of an interesting case to think about, because it really is, it's rigid objects, but there's a lot of diversity, but it's diversity that sort of, I don't know, we can kind of think about it. In fact, TRI actually has procedural dishes. I just absolutely love this, right? So we can actually, make, this is just a spline showing the geometry from one particular angle, but we can pipe that through a procedural CAD generator, generate like beautiful visual geometry and also simple collision geometry and mass properties, and it's good for simulation and it's good for rendering. And it's like a whole diversity of mugs that's defined by a handful of continuous parameters that define like those, what you're seeing there, those spline points. Yeah. So that's like a cool thing. So that means we don't have to, we can ask the question purely with models and in simulation, for instance, if we want to, and it's still a rich question. Oh, you know, by the way, for rendering, we have the material properties put in there, but you can also just texture map anything. They've got it to the point now where you can just take a picture of a mug and grab the texture map. It'll align the mugs to the data, and boom, we've got a new mug that we can simulate. It's pretty cool. I think that is going to be open sourced as soon as we can work it out. So there's no question of, yeah.
Sorry, there's a question on the chat.
Yeah. The handle is roughly a B-spline. It's a couple splines, but yes, it's a spline parameterized thing pushed into a procedural CAD software. Out comes the geometry, both simple and collision geometry and visual geometry. Sorry for the train. Okay, so let's think about what representation we could use for mugs, right? So we've so far talked about, like I said, one of the big ones would be if we have our sort of URDF file, then there's some frame of the object, and we're going to write X of the object as our canonical representation. But it's really hard to come up with the right pose that fully describes a whole category of objects, especially, so people in perception do this, and I'll show you some of the work from perception that are doing this, but it's hard to do this, hard to imagine that being the right idea for manipulation. So, if I care about exactly where the toe of the mug, the toe of the mug, the toe of the shoe or the tongue of the shoe or something like this, right? I might have different tasks that require precise knowledge of some different parts of the shoe. So trying to summarize all shoes with just sort of one canonical reference frame is very hard, I think. Right, so how do you even specify the task? What's the cost function? I think that's a useful question to ask, right? So I would like to distinguish between the questions of what do you need to execute the task versus the ones that you need just to even specify the task. Like how do you say what you want the system to do? Right, so I think we should separate between and I think this sort of specification language, sometimes people forget about it. We're so focused on thinking about the planning and control problem, but if you can't even write a cost function, then that actually is a showstopper for a lot of these problems. I don't know how to write a cost function for buttoning my shirt or making pasta, right? So what are our sort of candidates so far? I said we've seen a bunch of different representations, right? We've seen the pose, some canonical pose of an object. We've talked about just using point clouds, raw point clouds. What other representations that we've been kicking around here? There's others we've got in our pipeline. I mean, masks are an example, right? From the mask RCN and the segmentation. And actually, there's a really good one sitting there that's coming out of the object recognition, right? People do class general object recognition, right? We're able to identify goats and camels and whatever in the scene, right? So what representation do they use typically? What has been the successful representation? We can do masks, but there's another one that came even before masks.
Bounding boxes.
Excellent, right? So you can do bounding boxes. And bounding boxes are interesting because you can do them axis aligned, or you could do it with an oriented bounding boxes. And if I can fit like a shoe with a bounding box, if I can at least get a consistent orientation specification, then maybe the bounding box is almost good enough to talk about pose, right? So this is like close to some canonical orientation, right? So that's a good candidate, I think. What else have we seen? I guess we haven't really seen too much, but the sort of implicit in what we've done is there's just the question of shape, right? Which has been tucked in our URDF files so far, but you could imagine saying that the goal of the perception system should be to infer the shape of the objects of interest, like the complete mesh geometry, or or some approximation thereof, whether it's in sign distance function space or meshes or point clouds or whatever. And there is some interesting work that I will talk about in a bit about trying to do this, trying to do sort of shape completion. Somehow my angle makes me look like I have bad handwriting. Which is the problem of, for instance, taking an image in to a big neural network, for instance, and trying to guess the 3D geometry out. And there are some spectacular results in that. Okay, so I think any of these could be used. Some of these are sufficient to specify a task, but it's actually a super interesting question. If you think about the mug on the rack question. I've now just filled my tea, so I won't demonstrate, but let's say I had a canonical pose for all of those mugs, whether it's like the bottom middle of the base or something like this, right? Then that pose might be very inadequate for this, putting the rack on, right? So all I really care about for that particular task is exactly where the free space of the mug handle is, right? And there might be other tasks where if I want to put it in the dishwasher, maybe I don't care as much about where the free space of the handle is. I care about like the overall orientation. Scene graph-based representations. So what do you mean by scene graph-based representations, Dale? You mean?
I'm thinking like the mug is on the whatever, or things of that nature where they're actually describing relationships between the mug and the rest of the things, because that would be a way of getting to the handle is on the rack. But it almost requires the first question that you're talking about here to be solved. I don't know about solved, but it's yeah.
No, that's awesome. So if people got that, he's saying that you can specify some people will specify like the geometry of a scene in computer graphics, for instance, with a scene graph, where you might say you've got like it is the reason we called our system scene graph too, but you might have the world, and in there you might have like a place setting or multiple place setting, and then you might have a fork, a knife, a spoon, for instance, yeah, like this. And you can put relations saying that like the fork is near is part of the place setting, or the fork is on the table, or other somehow semantic or topological, let's say, representations between them. So that could be like a scene graph from computer graphics. And I think that is the representation that we're going to want for some of the higher level task programming that we're going to do. is something more at that level. But you're right. So I guess I'm asking in this case, I'm thinking about tasks that are a little bit more geometric in nature, like you have a precise geometric goal, let's say, but you'd like to do it over an entire class of objects. Right. I think the one thing seems clear is that whatever representation we're going to have, it's going to be task specific, right? It might, if I change the task, my representation might need to change. So if I just try to train a perception system all by itself, independent of the task, that serves every possible task, that seems wrong to me. You know, it's also going to be somehow dependent on you know, what the perception is capable of seeing, right? If there's partial observability or whatever, you can't ask it to know things that are unknowable. And it should also somehow depend on what the control system is capable of doing. There's actually, I kind of wish we had time for it, but there's a, like in linear Gaussian systems you can think about some of these things pretty clearly, right? You can think about like the way people do system identification in a linear Gaussian setting is with algorithms that we understand. We understand that it's still hard even in that case, which is a little frustrating. But at least the mathematics, you know, the formalisms are well understood. So for instance, people do these balanced realizations where they try to balance. You have a state representation that somehow balances the trade-off between controllability and observability. You know, so there's some need to somehow balance what the control system can do and what the perception system can do, and to capture the task. It's a very hard problem. It's such a hard problem. Okay, so let's talk about a few sort of approaches, right? So there are people that are thinking about how do you generalize pose to many objects. There's a subdiscipline starting, I guess, or that's around of, if you look carefully at the title of this paper, but it's category level, you know, pose estimation is a thing that you'll see papers coming up frequently on. There's a ShapeNet data set that's been very helpful for that kind of work. But for instance, if you take all the cameras in the ShapeNet data set and try to put them into some canonical bounding box, you know, axis aligned, orientation aligned bounding box, and then even apply like a color value in this particular case of that there might be some ways that you could somehow generalize the notion of the reference frame or pose to an entire category of objects. And then you could even correspond, once you put all of your instances into this sort of canonical frame, then maybe you can talk about you know, its location in the frame. It's just X, Y, Z location, which they've colorized for us here, as somehow being a way to correspond between different objects, right? So if I wanted to put the lens somewhere, then I'd be maybe looking for things in this part of XYZ space. But the handle, right? If you're trying to get the handle on the mug might be in very different, the handle of the mug might be in very different places in XYZ. So even in a canonical reference frame like this, even if these systems I think are well, I don't know enough about them to really say, but my impression is it would be hard to train something like this once you leave the ShapeNet world. But I think even if you trained it perfectly, it's not exactly that's the information that we need, right? To do something like putting the mug on the rack. But then every once in a while you see something like this, which is just kind of like, this is one of the ones that my perception friends showed me this morning. It's like, what? So they are doing roughly this canonical reference frame, and if you watch it go, they are saying, okay, we're gonna fit the shape parameters in some latent space Z and the rotation and the transformation simultaneously, and we'll take an image and we'll spit out this thing that's like not only the pose of the camera, but like the shape reconstruction of the camera roughly. And I don't know, like you see something like that and you think, that's incredible. If I can just look at a picture of a camera and get that much information out, then geez, we're done. So I don't know. Let's keep watching. I don't think it's quite a technology yet, but cool stuff is happening every week, right? Okay, so Oh, now it's gonna, okay. So here's a different idea that I think the work that we've been doing in my group for the last couple of years in this space is just going down a slightly different axis, and it's one of the ideas that's out there, but I feel like it's a good fit for the types of problems that we're trying to solve in manipulation, for a lot of the simple problems in manipulation that are very geometrically specified. Which is, you know, we're doing it in the context of like picking up shoes and putting them on the counter. Again, this is just the task.
Well, so I think you're on the whiteboard for the class.
Thank you. Did nobody see the camera get fit into place then? I guess people saw it, but let me just make sure people saw the important part if you're just watching my slides. So they took a picture of this camera and they inferred the shape and the rotation. Let me show the shocking part here. Yeah, they like fit the shape parameters to this camera, and then wow, it's really good. Okay, so the one particular representation of geometry that I think is nicely compatible with a lot of the tasks we want to do in manipulation, the geometric tasks, not like making an egg or something like this, but putting the shoes on the front of the rack or hanging the mugs on the rack, is to, instead of trying to use the entire geometry of the object or some canonical pose, they just label a handful of key points. Okay, I think my key point shiny key point thing is not working, but there's this other branch of perception research that has been trying to, it was, I think, mostly inspired by human pose recognition. And you'll see lots and lots of pictures and ridiculous movies of people doing being shot through the air and all kinds of stuff that where they have their you know, their pose being tracked, or they're dancing on the street, right? And they're trying to reconstruct the poses of the human. But the technology there started with trying to just recognize the location of a handful of key points on the object. They also have a graph that's connecting it, which is different. There are some places where that literature has departed, I think, from what we really want for manipulation. But this idea of like estimating the key point locations is super useful for manipulation. Okay, so you know, there's open pose was one of the early ones. And for the mugs on the rack, it's like exactly what we want. And I think for a lot of different tasks, it can be very useful. So how does that work? Is we would train a perception system to identify the location of a handful of key points. So we will have a human annotate a handful of key points, okay? And then have our perception system that takes the image in, spits out the estimated location of the key points out. That's the location of the key points is the thing that we hand from our perception system down to our planning and control system. And then we can actually just write our kinematic planning, instead of using the pose of the object directly, just say, I'd like to come up with some relative pose transformation that will move, let's say, this point into some desired location or desired configuration. So for instance, maybe the only thing you care about here is that the yellow point in the middle of the handle gets put aligned with the mug, or with the rack. Okay, so let me just say just a little bit about how those networks work. It's not, there's a lot of details that I won't go into, okay? But if you look at the way that these key point networks work, again, trying to get a sense of how much the world shifts in the last couple you know, months or whatever. I think there are a huge variety of architectures that people use for Keypoint networks. We kind of, I think there are a few backbone networks that are sort of similar to the way we saw it in MaskRCNN of a backbone network. So for one of them, for instance, would be this something called a convolutional pose machine. And you could think of that as sort of the big starting network. There's a handful of others out there, but there's some canonical sort of backbone networks for these architectures. But the way that the representation works is you take an image, put it into some big network, of course, okay? And then the thing that comes out is a stack of images, which, there's one image, one heat map per key point is the standard thing, okay? The desired image that you put here, this is the way they're typically trained, would have a color value at one point, which is exactly where the key point is. Maybe to make the loss function a little bit more smooth, we'll sort of put a few lightly colored points in the vicinity of this, and then no key points, no values everywhere else. Everywhere else is just background. Okay, and then you'd have another location on this, the location of the key point number 2, a location of key point number 3, all represented as a heat map. Now that's super interesting because the output of this network at inference time is now, in some sense, a probability estimate over the entire image of where I think that key point is. How many hand annotated images would you use in training roughly? For the KPAM, I'll show you the annotation tool in a second. It's actually a small number because we use the same trick of using one label to give many images. But that's a great question, okay? So, so we learned these heat maps coming out of the neural network, okay? Now there's a couple interesting things about that. Depending on how you train the network, you can actually train, you can have the ground truth can be for only the visible key points, or you can include occluded key points. So in the image on the screen, for instance, you can't actually see the, if I flip back here, sorry. You can't actually see the point, which is the center of the middle of the mug on the bottom in this frame, but we could still label it. And especially in the way I'll tell you about in a second, and for Tony's question, then, and we could still have the network try to predict in the image roughly where is that occluded point in the scene. And that's a useful thing, as long as you can label it well. That can be a very useful thing to have the network. Basically, it's doing a form of sort of shape completion where it's trying to infer where that thing must be, even if it's not visible. Or if your labeling approach restricts it, or if the task is better for the task, you can only label the, you can just have a blank heat map for instance, the occluded key points, and say that you should have an image, a heat map for only the visible ones. Okay, so let me answer, I don't know if maybe I skipped that slide, I'm sorry, but okay, so the way the answer to Tony's question, how many annotated images do you tend to use in the Keypoint network? So in the same way, we took our camera attached to the robot's wrist, made scans of the robot, did the dense reconstruction of the geometry, and then clicked once in our interface saying, here's a key point, here's a key point, here's a key point, and then back projected to have many rendered images with the ground truth key point label. And that's also how we could label occluded key points. So in practice, it was like a couple hours of training. They said it was like 3 hours of human time to label enough to get a very robust performance across a class of shoes and mugs and whatever. And this demonstration, if anybody was around when we were still on campus and came into the lab when we did our open house, whatever, we've had lots of people come through the lab and take off their shoe and put it on the rack, and it almost always like we'll put the shoe in the right place. There was sort of one exception. Well, sorry, the first time someone with really significant high heels came in, that one screwed us up, but we then scanned the shoe and added it to the data set, and it was all good, and then we could do high heels. And then the other one that got us was Daniela Roos, my colleague, had extremely, I think extremely expensive, but I hope we didn't hurt them, but extremely different material than I'd ever seen shoes, and that threw us too. So, but again, we scanned the object and threw it into the training set, and that's one of the amazing things about perception systems like this, is that you can sort of, when they do make a mistake, you can just get a little more labeled data, throw it in, and they kind of don't make that mistake again, you know, to some extent, okay? But all of that I was talking about is really about how do you even specify what you want to do. It's not enough to complete the task, right? So, but here's where I think for the simple tasks we were doing here, but we were doing them across the category, you could stick in a lot of the different approaches that we've talked about before. You could, for instance, once you've, if you have a segmented point cloud and you just take the point cloud, you could just look for antipodal grasps. Or you could look for, you could run some of the learned grasp metrics to look at the point cloud and try to tell me where on the mug to grasp, okay? And then once I make the grasp, it just becomes a kinematics problem of saying, if I assume that those key points are in some position relative to my hand, and that they will stay at the same position relative to my hand as I move through space, then it becomes simply a problem of choosing the gripper orientation over time to accomplish the task. Okay, so these can be combined with a lot of different other approaches. Then you do need more information for completing the task. And we really did run this a bunch, and with some absolutely ridiculous mugs. Like you can just get, you know, once you say like to your friends, oh, we're trying to test mugs, people bring in things, or you can buy on Amazon. We had, you know, things that came from the Disney store that just, you know, had no right being a mug. There were some things that were super small and some things that were ridiculously big. And typically, actually, our worst failure cases on the test objects were when the mugs were super small, because we hadn't had, there's like some kid mugs that just, we never had in our data set. Like this one on, I think that one on the rack is one of the kid mugs. And it still did fairly well, but I think when it got really precise, the out of distribution stuff got us. Okay, so if you just use the immediate point cloud, then there is some limits to what you can do. For instance, you can't do collision checking along your path with the you know, like say the backside of the mug as I'm going through space. So there's been variations of this. We did one that added a shape completion network, which are these, like, you know, you saw it in the camera case, but these sort of magical things which you show them an image and they spit out the 3D shape completion, right? And then if you add that, give that information also to your planner, you can try to avoid collisions, for instance. In the mug on the rack example, we had to be a little careful initially. We had to basically say we want the key point to be away from the rack over here first, and then take an access, you know, in this particular direction, because without knowing the mug, that strategy would work almost all the time. But if we didn't do that, then you could imagine just knocking into the rack on the way there or something like that. The same way we did with our pre-grasp planning in the original one. And there's more work in manipulation doing this kind of thing. This is one from Utah that's showing similar success using 3D reconstruction with a different network, point SDF. And it's just very cool to be able to take a point cloud, a very limited point cloud of this, and be able to pass it through some trained deep network and get complete geometries out, right? They're not perfect, right? But they're maybe good enough for grasping and the like. And they use that for their grasping pipeline. Okay, another cool thing is that a lot of the tools we talked about last time can be used in conjunction with sort of a key point based pipeline, right? So actually beyond my expectations, Wei Gao in our group has been doing like peg in hole tasks, and peg and hole these days includes not only sort of a traditional peg and hole in this case, but also like Legos are peg and hole, and USB sticks are peg and hole problems, right? And also this is sort of a wiping task like we talked about where you have to follow, but if you're using, if the peg you're sticking in or the thing you're wiping with has a category level of dimensions, and Legos are a whole bunch of different sizes, then how do you write even that end point controller? How do you do the remote centered controller, for instance, right? Well, if we assume that the mass of the object is small relative to the hand, okay, that is one thing that we're not trying to estimate the mass of the object yet. But it's surprisingly effective to just say, I have some tool in my hand now, and I would like to apply forces around the key point on that object, which I assume is rigidly attached into my hand. And then suddenly, you know, some of these tasks, which much looser tolerances than the stuff I showed you in the factory, but with loose tolerances, you know, oh no, where's my amazing video from? Wait, let me just see if that. Ah, man. Well, Way's got an amazing video, which I'll put on Piazza or something. I bet it's hidden actually. Well, imagine a robot sticking USB sticks in and Lego sticks and whatever, but at the category level. It's pretty good. So the key points are a super idea, but a very simple idea, and I think we should. I think it's not hard to appreciate where they run out of steam, right? But surprisingly useful. And for me, it's almost more of a lesson of don't ask for more than you need from your perception system, right? So if you're trying to ask for the pose, but you really only care about the location of the handle, then somehow you're making the problem harder for the perception system than it needs to be. Certainly asking for the full 3D geometry, if you don't need that, potentially much harder than it used to be, or than it needs to be. Okay, so the natural question that everybody asks when they see this is, okay, but you had to hand label the key points, right? And I think of that as a strength in some sense, because those hand annotated key points, which were done efficiently, are somehow a semantic label. So if you just look at the geometry, it would be very hard to sort of say, this is the handle, or this is the bottom, or this is the top. And the human can just add that semantic information, semantic meaning of some sort of human readable label, let's say, that would be a high level label that we could write objectives against. So that's I think of it as a very efficient way to add a little bit of human information to you know, make the programming of these things more general. But everybody comes in and says, but can you just learn the key points? And so I think that's it's a super good question, and people have been working on it, right? So in particular, if you can write tasks just based on geometry and not about the semantics of the task, but just the geometry of the task, then maybe there's ways you can do it without hand annotation. And so this is work called Keto. It's also using key point representations for tool use. Actually, the first author is now in AeroAstro here. But there's been a variety of sort of good work where people are extending the general idea of key points as the representation into tasks where you can, by executing the task in many times in this case in simulation, it can actually back out what are the meaningful key points. I encourage you to look at that if you're interested. And then we have a particular technology for doing it that runs through this idea of trying to build dense correspondence networks. So let me tell you a little bit about this one, since I know it well. Okay, so let me make sure you understand the images you're seeing here, because if you don't understand this, it'll get confusing in the next couple slides. So on the left, we have a still image almost, but I don't know if you noticed that just moved. Okay, so this is an image in a display, and probably Pete that day was moving his mouse over the image and highlighting a particular point on the image. Okay, in the middle here is a heat map, which is saying in a new image, the new image is on the right here, in a new image, where do we think that the corresponding pixel for that point is in the new image? So we remember correspondences from the pose estimation in the ICP lecture, right? It's just trying to find the point on this object that corresponds to the same, or in this point cloud, but in this case, it's an RGB image. It corresponds to the same point. So if we're doing well, then you should see, for instance, let me just run it again. So the bill of the hat here, if you can track the bill of the hat by drawing a consistent point in these different images, then you're solving the correspondence problem well. So the fact that this is putting up a heat map, which has most of its heat corresponding in a relatively small region, means the network's fairly certain. That's pretty good. And we're summarizing the peak of that distribution with this point over here. And in practice, we've been pretty happy with the results. This is, notice, a deformable object, right? This is actually deforming quite a bit in this scene. It's a non-trivial task. I'll tell you a little bit about how that works. Okay, so once again, the starting point has been to build a dense 3D reconstruction. So that was the robot moving around, just getting many scenes of the camera. And then we used elastic fusion in this work as a particular type of geometric reconstruction algorithm, which is just trying to fuse all those point clouds into a consistent geometric representation. Okay, now the idea, so in the key points, or in the, we've talked about this pipeline a few times, right? So the first one was, we called it label fusion, where we would then take our CAD object and click 3 times on the CAD object, click 3 times in the image, and that would be an initial guess for ICP, and then it would fit the ICP in and it would send back the labeled images, okay? In the Keypoint network version, we did this. We would do the dense reconstruction, and then we would click our key points, label our key points, and then back project, and all those images would have the labeled key points. In this one, we are just doing this, no human involved. We're just reconstructing. But what we're telling it is all those images, every place that was the same position in my 3D reconstructed scene, we back project the pixels and say those pixels should correspond to the same point. So basically, it's kind of like doing the key point thing, but it's doing it for every pixel in the image, right? In fact, the original cost function with this pixel-wise contrastive loss, which we could write down, but we actually have replaced that now with effectively the key point heat map loss function, and that works much better. So it's really like, imagine that every point in my geometry is a key point, and how do you train an image so that all of those images are labeled as the same point. Now, what is labeled in the same point? We're not going to actually have this ridiculous stack of heat maps. What we do is we have we choose some fixed number of dimensions. We call it the descriptor length D, okay? And we try to just say the value in this D-dimensional vector space is consistent across all of these different images. When D is 3, then we can just draw it as RGB, but in general, we can make D a much higher dimensional space, and this is just saying that should be the same point in the high dimensional space. Okay, so this is that the new loss function versus the old loss function, but again, it's this example now of we're mousing over here, we're seeing the corresponding point in this one, okay, and this is what originally was a very uncertain heat map became a very certain heat map, and that we were very happy. Now here's the crazy thing, and this is, I think, too good to be true, sort of, but somehow, if we do the training only like this, and we train one object at a time, then maybe because we've pushed this into just some limited dimensional representation, it tends to choose a representation that does a class general, a category level labeling of the objects. So let me say that again. So this is totally unexpected and surprising, okay? but that all of these hats are being colored the same color. So that's just drawing its position in the d-dimensional space. And the fact that they're similar colors for similar parts of the shoes is we've trained it on all of the shoes individually, but there was really no reason that we asked it to, we didn't ever explicitly ask it to use the same representation for bills of the hat on all the different images. It did that sort of automatically, but we exploit it heavily. Now this is something that, we should improve. If that stopped working, I wouldn't know what to do, but right now it's working very well, okay? In the case, if we wanted to do instance specific and force them to learn different representations, then all you have to do is put multiple hats in the scene when you're doing the training, and it will then, in order to satisfy that loss function, it will find a representation that separates those. That makes sense? I know I'm saying this at a high level, so please ask questions if you want. If I've left anything too vague. So I think the connection I wanted you to make here is that if I can train a network like this, which is a self-supervised, and I already said it, think of that as training like a dense version of key points, right? So I basically made every point on the scene be a key point, okay? And then the question becomes, if I if I need to down select it to make it useful for control, for instance, maybe it's too much to hand that every key point. Maybe they don't all exist. Then there's a separate question. But right now it's just the idea of having completely self-supervised dense key points. And even if you don't do anything more, just having the correspondence is useful to do some tasks. So for instance, without having any notion of object, any canonical CAD model, anything like this, if you just put the caterpillar in and click once on the image, just like they were mousing over the image and you could see the correspondence, you could say, just pick up the object here. Now we'll click on the ear in one frame, then you can put it down. He's trying to deform the object in different ways, and it'll just keep picking up the caterpillar from that point. So contrast that with the, our bin picking solution, which really had nothing to do, no idea of what it's doing with the objects. This has a little bit of information, right? It doesn't have any semantic information, but it has, it's able to sort of at least pick on one particular corresponding part on a category of objects. Now here's where it gets even more, I think off the beaten path from what we've been talking about in class. And since I have time, I will go into this now. Okay, so this is what I was talking about, where people who are training end-to-end learning really do train some perception-based network, some let's say the dimension of the joints coming in here, and a relatively small network that represents the controller, okay? And typically there's a relatively low dimensional bottleneck that people put in between, which is low dimensional because you want to be efficient in training the policy. If training the policy is considered harder because you have to do many simulations, or because you have to do many imitations or many demonstrations, then you want this to be lower dimensional. And the question is, how do you come up with Z? And there's a bunch of different approaches out there. People use autoencoders if you're familiar with that, but you don't have to know any of that for now. I think the idea that is maybe clear from what we have been talking about so far is that we can use those dense descriptors and just downsample them to pick a handful of key points as our correspondence function. But now, instead of having them semantically labeled, we're just going to pick a handful of points in our high dimensional space and find the closest corresponding point. In fact, if we just pick them at random, but not too close together, for instance, then that works surprisingly well. Okay, and we've done work to try to move them in the high dimensional space, but even if we don't, if you just have them sort of randomly chosen in the high dimensional space and find the closest corresponding point to that color, like you're choosing an RGB value, for instance, and trying to find the closest color in the image, that works surprisingly well. And we pick a relatively low dimensional set of those descriptors and push that into the policy. Okay. So this is just an understanding if we can use these tools in an end-to-end learning approach. Okay, so in this case, though, we're going to do, we'll talk first about what exactly we did, and then I'll tell you why we did it. But so this is an imitation learning setup. So Pete set up a keyboard and mouse teleoperation. He can do it, or he wrote a simple controller in simulation for sort of unit testing. But basically, you would do a handful of examples of let's say flipping up a shoe, which was we like that task because it's got some dynamics involved in it too. Okay, a handful of those tasks, and just asked, can we represent that Pete's behavior as a big network with a perception network that's doing the dense descriptors, a small downsample of those dense descriptors to the key points, and then pushing it through a relatively small neural network for the policy. Okay, so in simulation, super useful. Even so, this was kind of in the transition of people believing in simulation or not believing in simulation, I think, but the value of simulation came through, I think, in this, because we could train descriptors completely in simulation. They would work just in simulation. We would train them differently in the real world. We didn't have to try to train descriptors in simulation to make them work in the real world. But even in simulation, we could just hammer on different representational questions. How big should the network be? All the different hyperparameters of the network, for instance, learning rates and the like, and just basically write a hand-designed controller that would shove a box around or flip it up and ask, could we copy that controller into the network? And that was super useful to just kind of debug things and hyperparameter tune. Okay, and the result was that they found that it was useful to have some recurrence in the network. Now I feel bad not having talked about LSTMs or anything yet, but this is a recurrent network that has some amount of memory in it. So imagine your neural network with connections that feed back on itself. Okay, so the network has some amount of state inside it. And they're horrible. They are horrible dynamical systems by any sort of dynamical systems standard, but somehow they seem to work well for training policies like this. Okay, and then doing the same thing in reality with handfuls of demonstrations, like order 100 demonstrations per task. Then it got surprisingly good results. Okay, so this is, I showed you this at the very first lecture, just of the variety of things that I think we're just able to do barely in manipulation. And this is done with a big caveat of only, it works in the narrow case of where the imitations work. And if you were to ask it to do something outside of the imitations, it would fall apart pretty hard in an unintuitive way. If you accidentally came up and bumped the camera, I don't know. We haven't really tested that, but I know that Pete and Lucas didn't want people to bump the camera when we were doing the lab because they might have to redo their imitations, for instance, right? So, but in that space, boy, this thing looked super robust and super capable. So again, it was using the real-time tracking of those dense descriptors. And I think I have a couple of the results here. So this is the intuition. This is the only time we could really plot it was in some of the very simple tasks that were very low dimensional, like the pushing the sugar box on the table, where it was sort of reasonable to make a two-dimensional representation of the demonstrations of being the initial position or orientation of the box, for instance, and you ask, when did the network do well and when did it not do well? And the answer, the intuition, if you asked, I think Pete and Lucas, they would say roughly that when you're in the convex hull of your training data, when you're near one of the examples that the human gave, then it works incredibly well. And when you're outside the demonstrations that you gave, no guarantees. All right, so this is, I think, for me, this was shockingly good. And I think for a lot of people that came into the lab to see the demo, it's sort of just shockingly robust and good, right? That it's tracking dense descriptor key points on the plate. Even though there's rotational symmetry there, It was trained in such a way that that the network would reliably output key points that are in the orientation it needed, okay? And you can change the visual scene a lot. And because of that initial correspondence network being trained by itself over, with the self-supervised data, it was extremely robust to all the visual changes in the scene. And then it's roughly just playing back what it was told to do, but in a way that using those, it was relative to the dense correspondences, it could generalize in a pretty beautiful way. There's a subtle point in here about, I think, why this is working so well compared to some of the other things that we will see and have seen in manipulation. Is one of them is that it's a real-time, we call it visual motor policy, but the point that it's using the camera inputs on every frame to adjust its control decisions is very different than the canonical, look at the scene, do my perception, make a plan, execute the plan, and see what happens, right? You'll see lots and lots of videos of, if you watch robot competitions or anything like this, you'll see lots of videos of robot airballs, right? Where they'll perceive the scene and then, move over and just completely miss the mug and then proceed through the rest of the task as if they had the mug in their hand, and it's just the most painful thing in the world to watch. And so the fact that this is using the perception on every frame makes a huge difference in how robust the network can be. And it's a standing challenge of how do we do this with more rigorous control. Any questions? So the state representation, the answer to the state representation question that was used in this example was, again, key points, but now self-supervised key points in the form of dense descriptors, okay? That only works for some tasks, right? So we already, there's certain tasks that we already know that it's just not gonna work for, that the geometric information, there's no canonical geometry of some tasks, right? If I were to, even this pencil, for instance, right, there's rotational symmetry that would be very hard to put a canonical orientation on that. The plate was actually sketchy. That we were able to do it like this. It was trained in a particular way to make sure that actually worked. Certainly, if there are tasks that aren't even geometric, that's just not going to work, right? So, yeah, very limited in that way, but is super useful, I think, stepping stone. The imitation learning is also painful, right? So the fact that you have to demonstrate 100 times every time, it's cool that you can demonstrate 100 times and get a task to work robustly, but it's super annoying. A task that's not a good example of a task that's not geometric. Well, an extreme example would be like cooking or something like this, right? So that where the success is how well the food tastes at the end or something like that, or is the egg done cooking. But there's a lot of things in between. It might be that the forces I need to apply are I need to apply a certain amount of force in order to accomplish the task, right? If I can't just talk about it as relative poses between one or the other, then these things are not sufficient. I mean, there's all kinds of examples like that, but I think the question is, the visual motor policies in this case generalized to other box-like objects, a Cheez-It box, for instance, instead of the sugar box. I think absolutely yes. It's just a matter of if you added that to your training set. Yeah. I don't have a video of it here, but it does work. I think the really painful thing about the demonstrations that I want to make sure you appreciate is that if I have the same sugar box, the same robot, the same environment, but I just want to do something slightly different, then that means going back to the drawing board and doing a whole new set of demonstrations. And that is a significant problem with imitation learning and even with reinforcement learning when we get to it. Okay. Okay, so let me tell you one last piece of this, which is about trying to do it with less imitations. Okay, so by the way, that plate I wanted to remind you was like the plate pickup we saw in the sink, and we've been just working on that a lot. So okay, can we do more generalization outside the convex hull of the training set with less demonstrations? And the idea that has been very interesting, I think, watching this happen is using deep learning to try to predict the dynamics in this sort of this state representation that we're working with. So can we try to predict the future? The paper that they wrote on this was called Keypoints into the Future. Okay, so trying to predict how are the key points going to evolve as I make control actions. And the idea there is if you can learn a model of how the key points on the box are going to evolve, then that is something that does generalize to a new task. Okay, so I can spend some amount of time doing demonstrations to just learn basically the physics of the box, but it's now the physics of the key points. And this is a baby step towards what I think is this huge problem of trying to do of learning intuitive physics, or learning these physics on the approximate models. Okay, so same task, but now we're going to try to, instead of just learning to copy the demonstrator, we're going to try to predict where the key points go into the future. And then at runtime, we're going to, instead of just copying, just asking the network for my control action, we're going to do a search basically to try to find the control, a stream of control actions that will move the box where I want it to go. So I can generalize to a new task by learning a model instead of learning just the dynamics, or learning just the controller. Okay, and it does seem to work really well. This is the paper that happened right when COVID hit. So we have like more simulation examples than real world examples, unfortunately. But we do have, we have sugar boxes moving around pretty consistently. Okay, the problem, and we'll talk more about this, is that even though we can train deep networks to predict the key point dynamics, the planning part is actually still hard. So yeah, I've got a whole shtick on this that I will tell you at some point, but planning and control is still hard. So I don't want to leave you with the impression that that problem is solved. I think I have no doubt anymore in my mind that we can train networks to predict the future of the key points, but I am seriously concerned about how do we do planning or control with that representation. Does this also use LSTMs? So yeah, yes. The network for predicting was an LSTM network, yeah. And does the learn dynamics model take in the commands to the robot as part of the features? Yes. So exactly right. So it's taking the dense descriptors plus the commands, and instead of predicting the control action, it's predicting the next dense descriptor locations, for instance. That's the model. And then if you roll that out forward in time, then you can make a longer term prediction. Okay, so yeah, I in the sort of timeline of the class, I wanted to stop and do this as a reminder that a lot of the stuff that we are working with is limited to like the rigid object, the known object case. it's super good to know, we have to know it, but this state representation question and the more general versions of it are looming, and we have to be talking about it. And I don't think at the end of the course, I'm sorry to say, we won't have a super satisfying answer to this. This is research. So, you know, it's moving quickly, but still hard problems. The other thing I wanted to leave just a minute here at the end to say that we are in the problem set that was released yesterday has a part of that, which is your project proposal sketch. So we're starting project season. And just to say a few words about that, I think there's a diversity of people in the class. Some of you are like doing manipulation research as your main job, and you happen to be taking the class. And there's some people that are here without any robotics background. Everybody's awesome and welcome. But I think the way you should think about the project might be different. Let me use those two extremes as like as what you could think about for the project, right? So a common question is, can I use my research? How close or separate can my project be from my research? I think absolutely, like, connecting it to your research if it's relevant is awesome, and you should do that. I think the ideal case for me would be, you know, oh, I'm working on this problem in research. I learned something in class that I wouldn't have touched. I wouldn't have done that algorithm, or I wouldn't have tried that thing on my research if I hadn't learned this thing in class. And I want to spend my project time to try a slightly different version of what I was going to do in my research because of something we learned. That would be like the perfect way to blend those two. But I'm more passionate about you convincing me that you tried something and learned something about the class than about trying to somehow say it's exactly my research or not my research. I'm not as worried about that. I just convince me you learned something. And then for people that don't have a robot in their living room, then I think you can, we've got simulation to do lots of things. I think there are lots of references in the notes. We're going to put out a few specific project ideas on the website just as projects, but I think finding a paper, one of these, you know, watch archive, they're coming out fast, or we'll point you to some that you can ask us for some ideas, and just trying one of these algorithms out that we haven't specifically given you code for already in class is a great project. You know, exploring any of these ideas, you know, we will work with you to try to find the right level of you know, scope for the project. So it would be easy to propose something that would be way too big for the project. I worry slightly less about the other direction, but we'll try to give you feedback on, like, that would be really hard, don't go there, or you don't want to have to label that data set or something like that. And we are going to, next week we'll have normal lectures, but the following week we'll have, we're going to devote the week to meeting with everybody individually to just talk through what they're thinking about for the projects and how it's going. So we'll try to, it would be great for you to have, you know, questions and progress, but this week's problem set is to just figure out what the heck you're going to do. And we will budget time for you in the remainder of the term to put good time into your projects. You're allowed to work in pairs. I know it's a little harder to do that now. That's partly why we have the Slack channel. You could, I mean, if there's 3 of you and you can, that is one place where once you have multiple people working together, you have to be able to say, you know, I did something and someone else did something. So credit assignment becomes important in the group projects, but as long as you can do that, and if you can work effectively on Slack, if there's any way we can help you do that, just let us know. I'm also happy to have extra office hours for me, for instance, if you want to talk through some projects ideas this week, even this afternoon, I could do it. So ping me if you wanted to do that. And ask questions now if you have any general questions.
I have a question about, like, Drake's simulation capabilities.
Okay.
If we wanted to do, like, and we don't have access to a robot, so if we're doing our project in simulation, say we wanted to, like, make a difficult to model material, like if you wanted to fold clothes with a robot, can Drake do that, or is it like good enough at doing that it's a useful task?
I would say fold closed, no. I think, yeah. So I mean, we have pushed it to doing things like tying shoelaces as rigid serial links and stuff. And we actually have now, there's a new team working on soft simulation in Drake, but none of that is prime time yet. So I would say folding clothes, no. Unfortunately. Coming soon. Clothes are actually the worst case because not only are they deformable, but they're thin. So all the collision detection gets really, really hard. If you suddenly like penetrate a thin sheet and you're on the other side, your normals flip, then things go bad really fast. So cloth actually typically involves some cheating in the dynamics engine to do it well.
The only thing I'm aware of that does it well is super computationally expensive stuff that people use for 3D rendering or garment draping, and they don't tend to fold and self-interact that much either. So it's people have tried and everything is wrong in some way so far that I've ever seen. So that's what I've seen with cloth.
And Dale has worked on that problem, so he says that with some experience. So
awesome. Thanks.
But those are great questions. Yeah, I mean, if you can Drake do this, or is there another tool out there that can do this? Right. I think if using Drake is not a requirement by any means, but we can help you more if you use Drake. That's the thing. It's like it's just easier for us to know what's going wrong. But if it's I've watched people like use a different tool and it was no big deal, but they spent a week trying to get it installed and didn't realize this and that was not going to work, and it's harder for us to help. Do you have to retrain for any changes in the physical scenario? If you change the surface of the domino sugars box is sliding out. It's a really good question. So for the learned key point dynamics, I think, I mean, the simple answer is that if it's outside the training set, we have no guarantees. But if you ask me, I think because the examples are a little bit varied, I expect that the controller that's coming out has to be robust in some ways that would probably give you sort of for free some robustness to those kind of property changes. I think there's a basic lesson from robust control, which I think the reinforcement learning people and the learning community, I think, hasn't articulated it, but they're seeing it in their experience, is like robust control tends to try to model uncertainty and then prove something, but nobody actually believes that the uncertainty you add to your model in robust control is exactly the uncertainty that the world has. But there's something like just by trying to be robust to something, you end up being more robust to whatever is happening in the real world. It's like a regularization of some sort that makes just asking you to be robust. And I would expect that to be true here too. Is that just by virtue of doing the task robustly, if the surface friction were to change a little bit, it would still work fairly well, right? It would, for instance, I mean, if you think about the decision making that the network's doing, rolling out key points, if it's over predicting, if really the box doesn't move as much as you are predicting it moves, your controller is still going to work, right? You'll still accomplish the task for the type of tasks we were showing there.
Russ, I've thought about this a lot, and I do want to add that it's the controller can be robust, but it's kind of not possible to learn a general learned dynamics model out of key points if you're hoping to have like a generalizable model for how key points evolve over a category. That seems to be you just don't have enough information because that's actually a function of geometry and.
Okay, so that's a super good point. So thank you for saying that. So let me say that just in my words, but I completely agree. So like if you wanted to flip up the box, having learned a model of or let's say that if you were trying to flip up the box by watching key points, right? And then you change the box dimensions a little bit, it would not generalize well to that because somehow the key points, it would have learned a particular, it sort of implicitly learns the geometry of the task in the key points. And you just don't have enough information for it to generalize in that way. Super good point. Yeah.
I think a box is okay, but like a cup, like what if the handle is like open instead of closed or something, and then you completely miss it? It's very interesting.
Right. Yeah. Boxes are kind of easy, but the point is if the task is heavily dependent on the geometry and you've somehow encoded that in, I think you're right. Yeah. Okay, thanks everybody.
Thank you.
Oh, it's Russ